Hello, everybody. Welcome to another iteration of FOSS, the Functional Open Science Skills for AI and ML Applications. Today, we're going to be talking about training and testing models, and it's not going to be me to talk about all of this, but it's going to be my colleague, Dr. Mithun Paul, which has a background in machine learning and so much more, has been in the field for roughly 10 years and is able to talk your ear off regarding training, testing models, and everything that goes in between. Before we do get started, I do want to mention that all of today's and the past material, you can find it at the GitHub wiki. I'm going to share it with you in the chat. And as we do continue with today's workshop, links and chatter will also be sticking to the chat as well. So if you do want to review some older material, please do look at the material and recording that are posted within each week's entry. Today, it's training and testing models, and I'm gonna let Mithun chat more about it as he knows way more than I do on the topic. Mithun, the floor is yours.
Hey, thank you, Michele. I hope you guys can hear me. So let me just share my screen first. And I see a lot of familiar names, Aditya, Nitin, and Hari. So a lot of these contents might be familiar to you because I had this is something we have been covering in a lot of the other workshops also, including generative AI and the NLP for all. Can you see a screen which says Introduction to Deep Learning kind of thing?
Yes.
Perfect. All right. So I'll get started. So I'm also going to keep an eye on the chat window. But Michele, if there's a question on the chat bot, can you remind me? I can't seem to find the chat window.
No worries.
All right. Okay.
I'll make sure that the question gets to you.
Sounds good. Okay, so I just wanted to introduce start with introducing some of the big names that you have heard recently. ChatGPT, Meta, all the Google's latest models, Gemini, which is in here. But so right now, if you are a completely new person starting with using AI models, you might be all these kind of names. But then your confusion might be, why are we talking about training and testing and all that? So today's class is about understanding a little bit of history of how did we get here, where we are right now. And then once we understand what that means, we'll have more knowledge to play around with the systems like ChatGPT and GPTs and DeepSeek that's existing there. So I think so far in these lectures, you have seen computer vision-based examples. My specialization is natural language processing. So I will look at how these large language models do what they do from the perspective of natural language processing. Say, currently, or at least 10 years ago, there were different tasks which was given to AI machines. And these tasks were all separate. For example, this is one of my favorite tasks, which people who have been attending my lectures will realize I'm beating a dead horse at this point, is that for the people who are new, this 10 years ago, this was a typical task which was given to the computers. Here are a bunch of movie reviews, and the machine was supposed to say if the movie review belongs to if the movie review has a sentiment of positive, negative, or is it neutral? For example, if the movie review, or even in this case, I think product review can be, my experience so far has been fantastic, and the machine is supposed to say, yes, that is a positive review. If the review as a support team is useless, the machine is supposed to reply back that it is a negative review. So that was one task. Another task at that time was email classification into spam and non-spam. So as you know, right now, more than spam, the spam, non-spam issue is kind of solved, but the phishing issue is still a little unsolved because the creators of phishing emails are smart humans. Every time they come up with a new trick, which the AI is not able to catch up with. So that was also another task at that time. There were a lot of tasks like generating text content, extracting an answer from a text, and these were all separate tasks, including machine translation, which means given a text in one sentence, how do you translate that to another? So then 10 years later, currently we have one single model which does all that for you, which is what we call large language model. And that's where the word large kind of encompasses all these different tasks that all these models can do. And you might have heard the term foundational model also. So in today's class, we will look a little bit deeper into understanding how do these things work in the inside. Like I said, this is you don't need to know this to access any of the GPT models and start working on it. But knowing this will really help you play with these models and understand how you can utilize them for your own purposes. So how does deep learning work? So term deep learning again was coined like 10 years ago to denote the depth of a neural networks. And neural networks, I was told you guys are introduced to the term neural networks, which is a collection of neurons. But the exact technical term is artificial neural network, because the current neural network is nothing but a software equivalent of what we know as the original neural networks, which is our brain, right? So to understand how do neural networks work, both in our brain and in its software equivalent, I have an example, which if you have seen it, just don't answer it. This is for people who have not seen this example before. The question is, where do you see the sign almost on a daily basis? And while you do that, I'm going to smartly try to find if I can find the chat bot. All right, nope, I can't see to find it. Please answer in the chat bar, or you can unmute yourself.
I don't see any. I don't see any comments in the chat, Mithun.
All right, then that's okay. I'll just move on. So it's mostly because some of them have seen this before. So this is the cruise control, which we have in the cars. And cruise control is, if you ask me, one of the original examples of how neural networks work. And how do they do that? So for example, if you set a particular speed you tell the machine or the car that the expected speed is 41 miles per hour or kilometers per hour in this case, and the car is currently going at 42. The moment you turn on the cruise control, what it does is a phenomenon known as feed forward and back propagation. What does that mean? It means that immediately the first thing the car is going to check is, what is my current speed? So it realizes my current speed is 42 miles per hour. And then the next thing it checks is, what is the expected speed? So the expected speed is something human set, which is 41 miles per hour. So the machine starts thinking, how can I bring my current speed down to the expected speed? So, and the answer is backpropagation, which is a very fancy term to simply explain what we just said. Or in other words, you might have seen this in your undergrad degrees if you took courses like control systems. All of this is nothing but a constant feedback loop. So there's an input, which is the user says, hey, here is my expected speed. And there is a signal which the machine compares with the current speed. Say if it's 42, all it has to do is reduce the speed once. Sorry, press something. But if it is not 42, if the current speed was, let's say, 45, it has to go back into the same feedback signal. You keep reducing, and then you finally hit 41 and you exit the loop. So that is how all these control systems have been working. And we are going to look at how neural network particularly is going to train this using these concepts. Okay, Michael, I just realized, did you want to stop and restart the recording, or is it okay?
You can go right ahead.
All right, I'm going to keep going.
Yep.
Uh, so what is the meaning of training a neural network? So let's get into the details of that. So neural networks, as you can see here, is based on neurons, which is inside our brain. And if you look at every single neuron, you might remember this from your high school biology. These little things, I think, are called dendrites, these little hairy things on the main control panel. And the big long line is called axon. I mean, even if I don't get the names right, the concept is that it's very similar to what we saw in the previous slide of control systems, which is on one side, we are getting inputs, incoming inputs to a central processing unit, which is one neuron, which now tries to analyze that signal and send it and decides which one of my output nodes should I send it out to. For example, the software version of the artificial neuron. Oh, looks like I got the name right. Dendrites, there's a nucleus, this is axon, blah, blah, blah. The artificial neuron is nothing but exactly the same thing. It gets these multiple inputs coming from multiple places, the most likely the neurons before it. It does some sort of a calculation and decides where I want to send the output. So now, how does that work in creating such a magnificent device known as neural network, which potentially now can do great things, including identifying pictures of cat, which is quintessential for human existence across all these years. So how does it do that? So in the previous lectures, you had seen all the image segmentation and things like that. But the idea is something like this. So initially, we take a collection of neurons. And when I say collection, it is a two-dimensional collection. So you can decide, you as a user can decide how many layers of neurons do you want. That is the first factor. I want to call it the x-axis. And you can also decide how many neurons per layer do you want. So you might ask, but what is the logic of how many neurons should go in one layer, how many neurons should go in another layer? The short answer is nobody knows. Even now, even like 10 years after the first 10 neural networks were used, nobody knows. What people have been doing is they kept playing around with this, mixing and matching the total number of neurons in every single layer. And then they suddenly realize, oh, in this particular task, this particular combination seems to be doing well. So as humans, we have this tendency of, or especially computer scientists, we have this saying that if shit works, don't touch it. So that is exactly what humans did, which is, hey, this is working, it's giving the answer right. So we are not going to ask, why is this particular exact combination good? The combination of neurons interconnected good. So if you hear the term hyperparameters, it's nothing but one of these things is like what combination of neurons is neurons per layer is good for a particular task. Or in the case of large language models, they started asking the question, what particular combination of neurons per layer is good for doing all these tasks together? And hyperparameter search, or you might have heard of grid search, is nothing but two for loops sitting inside the code after you create the neural networks and trying out all possible permutations and combinations of these neurons and trying to decide which one gives me the biggest accuracy. All right, before we get into the details of accuracy and all that, let me introduce the problem. The problem is here are a bunch of pictures. There are 4 pictures of dogs and 4 pictures of cats. We want to first train a machine to do something. Now, I want you to remember, if we went back to the old example of, let me see, the control systems, let's see here, right? So in the cruise control, there really is no training, right? This is something what we call live systems. Like it's just a if-else loop. There is no learning which you use later, right? So give me a second. In short, even though I said neural networks kind of systems have existed since long time ago, the truth is these things were not learning anything. They were exactly doing what it was told to do, which is, hey, if the speed is 42, my job is to reduce the speed, so I will get it to 41. But going forward, neural networks, on the other hand, are very interesting in that sense. What we do is, in the first pass, what we call the training pass, we give it a bunch of data. So usually, let's say you have 100 images, like images of cats and dogs. The first thing we do is we divide them into 80, 10, 10, 80 percentage, 10 percentage, 10 percentage. Now, what does that mean? So the idea is that the 80 percentage is training data. So if you have, let's say, 100 pictures of cats and dogs, we'll use 80 of those mixed pictures as training. 10 of them is what we call dev, and another 10 is what we call test. So why do we need to have this kind of an approach? Oops, sorry, system. Sorry, screwed up something. Give me 1 second. There's some tech issues going on. For a lot of people here, even though you have attended some of my previous lectures, I want to ask you the question of why do I have to do this kind of division between data? Why do I need to train, dev, test, and all that stuff? As compared to, let's say, control systems, why can I just not have a rule which says when X happens, do Y? Okay, I finally found the chat window. So either answer in the chat or unmute yourself, please. I prefer unmuting, that's faster. Oops.
Hi, Vachan.
There's some microphone on somewhere. Okay,
Yeah.
yeah, go ahead.
In the live control systems, like all the logics are like static. We don't change anything. But in this deep learning, machine learning kind of things, like we will train the system using the data, and then we need to evaluate how well we trained it or the model learned it.
Yeah, almost right. And I'm also going to read the answer Brandon said. Doesn't this tune the parameters? Kind of right. John just says, I just got here, but my hunch is to facilitate evaluation. If you test on scene data, you can't properly evaluate the inference. So yes, all of you are right. The thing is, if you are looking at the control systems, every machine has the same control system. And I say machine, if irrespective of whether your car is Toyota or Honda or Subaru, you are going to have the same set of control systems, which is a set of hard-coded loops, which means there is no learning here. We are not asking the machine to, hey, go train on Toyota so that we can reuse you in Subaru. So there is no generalization which the machine has to do. The input remains the same, the output remains the same. However, in the case of, let's say, cats and dog pictures, the very interesting part of neural networks, or what we call learning, comes from the fact that, let's say my 4 dog pictures here are only Labradors, and my 4 cat pictures here are only tabby cats. But when finally I'm going to ask the question, here's a picture of a retriever, the machine must be so smart enough to understand the underlying properties of what makes a dog a dog. So you see how the control is going away from the control system to a machine which is a human-like system. Because if you turn around and ask yourself, if I show you a picture of a Labrador dog or a retriever dog, your brain across all these years have learned both Labrador and Retriever are exactly the same thing because they all have the same set of features. So that is how historically neural networks and machine learning started saying, hey, so why don't we have a set of rules and we tell the machine, task one, identify dog. So if you remember your object-oriented programming classes, you will have learned things like dog has 4 legs, cat has whiskers, dog has long ears. Those were called properties. So until 2013, people were trying that what we call manually curated rules. It's called rule-based systems. So then can you imagine what was the main problem with creating rule-based system like that? Like me as a human was sitting and identifying properties which was uniquely defining a cat or a dog. So what was wrong with that methodology? Any guesses? Why can I not have a control system like setup where I have 10 million rules saying here is how a dog is defined. If it has long hair, 4 legs, if it barks, it's a dog. Why not? Why not use that now? Okay, since I don't see any answer, I'm going to say, I'll give the answer, which is that is not a scalable methodology at all. Today, you're dealing with cats and dogs, but tomorrow, what if the pictures are of motorbikes and cars? Right? So humans, as we grow up, we see a car, we see a motorbike, but somewhere deep inside, we are understanding, oh, this thing is different than the other thing because one has 2 wheels, the other one has 4 wheels. The cat is different than dog because it has X, Y, Z. So initially, scientists thought, let's try telling the machine every single property of every single object on Earth, but that was a completely intractable problem. You could always find one single new object which somebody did not have time to write rules for. And plus, the other thing is, what we as humans can express through our words is much limited than what our brain deeply understands. So the thought there was, how can we communicate what is inside a real neural network, which is your human brain, and that communicate that into an artificial neural network? So long story short, that's why we came up with this whole idea of training, dev, and test set. Now, what do I mean by training data, devs data, and test data? Training data, this is like a thumb rule or like a good pattern you need to follow. And here's the reason. In training data, out of, let's say, 100 pictures of cats and dogs, we pick just 80 pictures and give it to the machine and say, you do whatever you want to. Like, I'm not going to explicitly say a cat has whiskers or dog barks and all that stuff. You go figure out. I'm handling the control over to the machine. And I'm saying, you go figure out. But here are 10 pictures of cats and dogs, which you're allowed to verify your findings over. Now, remember that's 80 plus 10, 90. Then there are another 10 pictures, what we call hidden data or unseen data. And this is where people get very creative. You can say that my training set, I'll have a lot of Labradors, a lot of poodles, and a lot of cats, a lot of tabby cats. And the first thing the machine was doing was it starts memorizing, okay, this picture, answer dog, this picture, answer cat. But then we present a dev or test set, which is even the dev set the 10 pictures the machine doesn't know during training. And the idea is that we want to force the machine to stop looking stop looking into overfitting, which is the machine was capable of looking at a Labrador and say, oh, it's a Labrador, it's a dog. So it was memorizing some features. But we wanted it to distill, and get to the level of some underlying patterns, which our human brain normally understand, makes a dog a dog. So your dev sets usually were so nicely created that usually you never have a single dog which belongs to the same breed that were there in the training set. Like I said, if the training set was a lot of Labradors, dev set will be only retrievers and test sets will be only Chihuahuas, right? And what happens during training is every time, the very first time we give all these pictures, we ask the neural network, hey, here, this particular picture one, what do you think it is, dog or a cat, right? And the machine randomly, like at that point, tosses a coin, picks a random number. Even though it was a picture of a dog, it says it's a cat. Then what we do is we exactly do the back propagation idea, which is we tell the machine, oh, the output that you told us is wrong. What we want you to do is go back into your tons of neurons and do some sort of self-reflection as to why you said this is a picture of cat, while actually it's a picture of dog. And remember, we're not even telling the machine like, hey, you said cat, but this thing barks, so it's a dog. No, we grew beyond that. We said, okay, not my problem. You tell me what is the underlying pattern. So people discovered that the more times you ask the same question again and again to the machine, slowly the machine or the neural network started understanding, oh, what the human wants is not me to does not want me to memorize this as picture of dog, but it's asking me to find some sort of underlying patterns, which in other words are equivalent of the weights passed along these neurons. Now, what do I mean by weights? So remember our very first picture of our biological neuron, what it does is it takes inputs from its neighbor and it decides how much of the input data should I give it to my next level neighbors. And that how much, which is what you can see is called W1. The standard notation is W1, W2, W, etc. X1 is the data and W is the weight. So we force the machine and we ask the machine, like, you decide how much percentage of data at every single neuron or weights do you want to propagate to the next layer so that you eventually get to the right answer, which is dog. So as you can imagine, this process takes like millions and millions of feed forward and back propagation. It's almost like teaching a kid like, okay, no, this is the answer. Get me the right answer, get to the right answer, get to the right answer. And that is simply neural network training in a nutshell. So remember, the right answer is during training, we already give it the right answer that this is a cat or dog. So after, let's say, 10,000 such iterations, we also want to parallelly check if the machine is memorizing stuff. So remember, the dev set is, like I said, usually hand created to be much more tougher than the training data. So after, let's say, every 1,000 times you do the passes, feed forward and back propagation, we compare against a dev set. So it's literally a development set, okay? So and the reason is that machines have this tendency that otherwise, if it is seeing data which it has already seen, neural networks are very smart. It'll start memorizing this picture is dog, this picture is cat. So we have to force it to generalize. So that was second trick, which here, this is a very standard graph. So what happened here was the y-axis is error, like how much error is there between the predicted value and the original value. And the x-axis is the number of iterations. So what people started noticing was that the more data you give, the more number of dogs and cats pictures you give, the error reduces. It keeps reducing, keeps reducing, keeps reducing. And accuracy is the 1 by equivalent of error, inversely proportional, which means the accuracy of the system kept increasing until it reached close to zero error or 100% accuracy. So initially, scientists were really happy. Oh my God, this thing has 100% accuracy. I just have to keep doing maximum number of iterations possible. But then they realized there is a point of no return after which the machine is doing, or the neural network is doing nothing but just memorizing. So how do you say that? I'm saying that because in case of training set, I provide the answer explicitly to the machine that, hey, this is a cat, this is a dog. So as a smart child, the machine starts saying, okay, this picture, I'll memorize all the 80 pictures. If they show me any of the 80, I'm exactly answering correctly. But then we bring in the dev set, which it has not seen before, and we never tell the machine like, hey, what the right answer is. We are simply saying, in the dev set, which is a completely new set of pictures, you tell me what your accuracy is. And that's where we saw that there was an inflection point where after which the training set, it was continuously like memorizing, oh yeah, this picture I've seen before, this picture I've seen before. But in the set of pictures, what we call validation or dev set, the error was increasing, which means the accuracy was reducing. So in short, people realize during the training, we need to have constant check with images or data for which the machine does not know the golden answer, whether it's a dog or cat. Otherwise, it's too smart to memorize. So that's why we needed to have all these tests, so all this training and dev data. Now you might ask me, what is test? When 10 years ago, when we were writing neural networks by hand, like we wrote large language models by hand for my PhD thesis, at that time, testing is the 10 set of pictures which we never touch. We, even as humans, don't know what the test contains. And there is a reason for that. If I knew my test has 8 pictures was dog, if I as a human knew that, and I'm trying to create a new model and submit it to a paper and a conference, I will of course be biased to like cheat myself and say, oh, if nothing else, I just need to, if I answer dog, 80% of time my answer will be right. So what we did was we took the entire data, shuffled it randomly, and then we did the division of train, dev, and test. It's usually 80% will be training data, 10% is dev. And the 10% test is very, very secretly guarded. We even like hand it over to like other people so that we as the person creating the model does not have access to the test data. So remember, after shuffling, maybe it's like 10 power 6 data points of cats and dogs, pictures of cats and dogs. I myself would not know which was the 10% which had test data on it, or which the images which made it into the test set. So when do we use the test set? The test set is used just before submitting the paper. And that is like the true healthy way of, or there's no cheating there. Even if my machine gave like 99% accuracy on dev, it might not give 90, it might give only 95% accuracy on my test set. But that is the real answer you're supposed to present to the user, because that is a set of data which is very reflective of real life data that I might encounter in the wild or in the internet. But you must remember, all this was happening before the whole idea of large language models came up. So in today's world, you really don't need to do any of this. Why? Because currently, large language models, all they do is, instead of 100 pictures of dogs and cat, it takes all the internet. The companies like OpenAI have resources to run training over, let's say, what do they call that? 73 billion parameters. When they use the word 73 billion parameters, they're simply saying my neural network has 73 billion neurons, or even 73 billion lines coming out of it, the weights. So you can imagine the sheer amount of permutations and combinations that is needed to go through for the machine to finally arrive at the right answer of anything seen on the internet. Right? So large language model is nothing but something that was trained kind of like the cat and dog, but on the whole internet. Now, one more point which I wanted to mention is So in 2013, what we were all doing was, let's use neural networks, code it line by line. Let's put first 10 neurons in the first layer, 20 in the second layer, etc. But in 2017, somebody came up with this idea called transformers. This is the movie Transformers. This has got nothing to do with AI. But this was a neat trick. It was a neat trick or a collection or an architecture or a combination of neurons. It uses something known as attention and a bunch of cleverly crafted loops. You can, if you read this, I know it's not clear. It says feed forward, a bunch of these. They came up with, let's say, a small black box to replace the neuron. And they proved that this black box, also known as the attention head, is much more powerful than the individual neurons. And then we created collection of such black boxes. These little things were called attention heads, and then the collection of them were called transformers. The very first thing was called BERT, where the T stands for transformers, and I can't seem to remember the rest of the expansion. But that was the starting point of large language models, that we realized we as humans don't need to worry about how many neurons go into how many layers, but now the focus shifted into how many attention heads goes into every single layer. Long story short, people started doing mixing and matching, and then these great companies were all working on it. And that's how you ended up getting all these initial models like GPTs and BERTs. And this ends in 2021 because it's an older slide. But you can add like any of the new models, Gemini, DeepSeek, everything, every single thing is a nice smart combination of a transformer. So then you might ask, so how is Gemini better than DeepSeek or DeepSeek better than Gemini? It's nothing but they kept playing around with the architectures and found that, oh, if I use this combination of so many transformer layers in the first layer, so many transformer layer in the second layer, it is giving a better result or accuracy in a bunch of these tasks. And now there are these remember the cat dog classification. Now there is a collection of data sets known as MMLU, which is if you are building a new large language model, you need to have at least 95% accuracy on all these different kind of tasks, including, remember, like I said, sentiment analysis, or it could be paraphrasing and all possible tasks. And DeepSeek, for that matter, did not have any innovation as far as the architecture was concerned, but instead they said, hey, can we run this over floating point of 8 instead of floating point 32? And they said, okay, instead of 3 months, my machine trains on 1 month. So that, as you can see, if you have been following the rat race, you'll realize it's just a matter of people trying to reduce the training time, etc. Now, why am I telling you all about training and testing if we as normal users don't have the ability to do that? Oh, by the way, I should say common man doesn't have the ability to do that, but people in University of Arizona do, because we have AI Verde, which has one of the most powerful hardware devices in the world. So you are allowed to, if you want to create a large language model from scratch, you can do it. But it's a huge effort, because then the immediate question is, where will you get your data from, right? So nowadays, what people do is we take a pre-trained model, which in other words, let's say this particular leftmost picture image is what you would know as DeepSeek or Lambda or whatever. It's trained on a huge, gigantic data set, otherwise known as internet, and which is what we call the base LLM. And what people are doing is they take this thing and do a couple of different possibilities with it. Let's say you have a general model, which is the large language model trained on so many different tasks. We have 3 options. And you are a person, let's say you are a doctor who has a set of this is something we created for even John, who was in the class, that John had a specific set of data and he wanted a chatbot which was trained only on that data, but still he wanted the chatbot to retain all the capabilities of pre-trained models, which is knowledge it gained from learning over the internet. So how do you do that? The first option is retrain the entire model on your specific data set. But that is a bad idea because remember, your pre-trained model was trained on over 10 power 9 or 10 power 20 data sets, while now you're saying let's retrain it only on your 100 little cat dog data set. So the model is going to lose everything that it learned from before. So almost nobody retrains a well pre-trained LLM these days. What we instead do is either fine tune it or do something known as retrieval augmented generation. What do I mean by this? Fine tuning is exactly what the name says is we make the big base large language model focus on a domain specific data set. Like let's say rare diseases, or you are a professor in a class where you're teaching a class where only you have access to this set of slides and you want the machine to answer questions only from those slides. So we either fine tune it, which is in a way retraining, but we make sure the original knowledge or the original weights. So remember, when I say training, at the end of the day, only thing the machine is learning is I have these tons of neurons inside me. How much weight do I give for every single line that's coming out of every single neuron? So when people present you a pre-trained model, all they are doing is they'll give you a big spreadsheet of weights. And what they are saying is if you exactly maintain the weights, if you tell these neurons to, you remember this picture where we had W1, W2, if you can build a software equivalent of what we have, anybody can build a neural network, but the secret sauce is the weights. So the
Mithun,
weights, yeah.
there is a couple of questions, and one is a
Oh,
bit
in the chat.
older, so maybe we need to go back to it. So Nitin is asking for one, what about GRPO?
I don't know what GRPO is. Can you expand it? I can't even see that. All
Sure.
right, I learned.
Relative policy optimization, which is used in or DeepSeek math.
I don't know. I have to go look for it. I don't remember this. Yeah, okay, so DeepSeek, yeah. I was just saying this was a little exaggerated. Definitely DeepSeek has its own innovations, but I'm saying the actual innovation when compared to using like a attention layer, now it's all optimization. They're trying to make it run faster. So yeah, I'm sure I take it back. So they do have a bunch of tricks and traits, but all I'm trying to say is when compared to the original invention of attention, these are all like little tricks people are playing to get it more accurate and faster. So, what is the second question? I can't read it. In fine tuning, what?
In fine-tuning, how do we make sure the model doesn't forget what it was pre-trained on, since the
Yeah,
weights
that's exactly what I was saying. So here, initially the model was pre-trained and it remembers all these weights, right? 10 power 9 neurons, and it remembers all these weights coming out of all these neurons. Now, when we go back into fine tuning, we have to tell the machine that do not update all the embeddings. So this is what we call embeddings. In other words, the weights have these terms. It's a question of can you edit the weights or can you not edit the weights? So during fine tuning, we limit the amount of weights it's allowed to update. By limiting it, we kind of ensure that the machine is focused only on the small amount of data and not on the entire data. But again, like I said, even fine tuning, people don't do it a lot because of the lack of resources. Everybody uses something called retrieval augmented generation. And this is, if you ask me, is a very smart hack. The original model, which here the base pre-trained model is frozen, like we don't touch it, but we don't even fine tune it and update the weights. But instead, what we do is we add another layer So if, as you remember, everything right now is a question, answer, and prompt. So if the user asks one question, let's say, where does the sun rise? Or let's say we have a particular class on University of Arizona. Here's a professor teaching on a very particular niche class on rare diseases, a course on rare diseases. And if you ask a pre-trained model, what is, how does the rare disease for rare disease XYZ work? The model might not always know the right answer because remember, it has the knowledge of 10 power 9 data points, of which a rare disease is literally rare. So it might either not know the answer and it will start hallucinating, which is coming up with a set of answers. But when we do RAG, what we are telling the machine is, I'll take the question, what are the characteristic symptoms of this rare disease? I as in a piece of code wraps that question in another question, which says, hey, LLM, here is a question, which is, what are the symptoms of this rare disease? However, I do not want you to answer using your inherent knowledge, but I want you to answer only based on this database I'm providing. And this database will be your retrieval, the particular course material, which we are providing to the large language model. So we call it almost like collapsing. It's like LLMs are something with a huge amount of knowledge. We are making it collapse or focus on this very little set of data set. It is allowed to use the logical and analogical capabilities of what it learned from the entire internet, but it is not allowed to use the knowledge. But instead we say, if you don't know, or if you cannot find the answer in these particular texts, we force you to say, I don't know. So then that is the prompt which gets sent into the actual large language model. And the model is now forced to focus on this particular text. And whatever response it gets, we send it back to the user. So remember, if unlike the previous case where it knew everything under the sun, it was probably good at a bunch of general tasks. So we are now making it focus on a very specialized task. So if you look at the history of AI in the last 10, 20 years, we started as thousands of different models which were capable of doing independent tasks. Then we combined them all together to create a large language model. And by doing so, the model became so smart that it learned something which we still don't know what it has learned. It's projected into a higher dimension, and it is able to find patterns which human brain cannot. And then using those inherent knowledge, we are again asking it to force on a very small particular task or a domain. So this is what we call life goes full circle. But anyway, we are almost out of time. I wanted to give you some demo or at least code what we have right now in our repositories. I don't think we'll have enough time to run it all, but let's go to github.com/UA data lab. So let's see if I can do that back up. My keyboard refuses to work. All right. And this is the same GitHub link I think Michele had posted earlier. If you go to the home page of, where is that? All right. So if you can go to data lab, Force AI ML training, leave page. So I think this is the link Michele posted earlier, Force AI ML. I have uploaded 2 IPython notebooks. I want you to ignore this one with uppercase V validation. But the 2 ones for today is validation and test sets. So this is a simple example. This is a well-known example which has been around for 10 or maybe a decade or 2, where the goal is you are given California housing data set, by which what I mean is it's a data set that looks like this. So this data set was created 20, 30 years ago, which was, here is the latitude and longitude at which a house is present. What is the median age of the house? I'm assuming it's the age of the house and not of the people inside, because it's 15 is the age. What are the total number of rooms? What are the total number of bedrooms, population, households, median income, median house value? And I think this total training data was 17K. And the goal here was, as you can see, there is test set, right? And what people have done is typically they take the entire training set and separate a 10% of it as validation or a dev set. And the goal here was, given all this value, I will randomly pick a test set, a house from this California housing set, and I will not show you the value of the house, right? 94K. But your job, or you as the machine's job, is to accurately predict what the value is, right? So this was one of the very oldest, maybe 10, 20 years ago, this was the original training data set which people were experimenting with. So if you look at like even the code is there, and if you really want to have a look at I'll let you open up the test set, and most likely the test set does not have the gold answers in it. And everything else here, I'll just quickly run through it. I think scale factor is more to do with human readability. So we did not want it to be 94,600. I think that's why they're dividing it by 100 or 1,000. Now it'll be 9.4 or something like that. Now, everything else here, like remember, this is all happening deep inside your large language model, the training and stuff. So, which is the other reason why I'm not going through this line by line, because nobody does training anymore on your laptop. So deep inside what they have things like, let's start from the main and start tracking back. Meanwhile, okay, also you can just, if you go to the top of it, you can open it in Colab and just go runtime run all. So that can run in the background while I explain the code quickly. So here, all it's doing is load the training data, which is a collection of data about houses in California. I'm going to try to find main. Okay, so there are a couple of these things known as hyperparameters, which is learning rate is something which is more like, hey, how many steps should I take in one go? It's a little complicated math thing I'm going to ignore right now, because you don't need to know that explicitly, because you most likely will not train a neural network from scratch. Epochs is the number of iterations, and batch size is how many of these data points do I want to look at in one single pass, do I want the machine to look at. Validation split 0.2 means 20% of this 17K data will become my validation or dev set. So the first thing they do here is, what is my feature? What is my label? So essentially, neural network is nothing but given two things, A and B, find me the patterns between A and B, or what is the relationship between A and B. In this case, the relationship is, I will give you median income of a house. You need to tell me the label, which is my house value, right? If somebody asks you, give me one line explanation of what a neural network is, it just finds pattern between any two features. In this case, like I said, income and house value. So here, if you look at it, the actual code is just 3 lines: build model, train model, plot the curve, right? So let's look at first what the build model is. Build model is, in this case, they use a tool called Keras. Mostly people use PyTorch, JAX, or Keras, or TensorFlow these days, all different tools used to create the same thing, which is here is where it's creating the sheer amount of number of layers. And in this case, it's a very simple. It has only one neural network, and the shape is only one layer. And here we use concepts called optimizers, which are like mathematical stuff. Loss is what we were seeing. The goal is to reduce the loss. Remember, the graph we had seen earlier was to reduce the loss between what I am predicting and what the actual goal value is. So let me see if I can quickly pull up that loss picture here. So loss are also known as error. So that there is loss as error, and the goal was to reduce the loss. And how do you reduce the loss? For which they use least mean squared error, which is what is the difference between my predicted value and the goal value in terms of the distance between them. And you can read on what a loss function or an error function is. Now going back after creating the model, the next thing is train the model. As you can see, train the model is nothing but a model.fit code, which in most of Keras provides it as the abstraction model.fit. And if you open this code up, you'll see all it is doing is backpropagation feed forward, backpropagation feed forward across my underscore epochs, which is 30 epochs, which means 30 times it will go forward and backwards, taking batch size at a time, maybe 5 at a time, 10 at a time. At the end of which, now the model is trained, and see the word wait. That's all we hand over. We used to hand over to our next partner. We'll say, hey, here's the CSV file which has the weights of every single neuron. Just load the weight. So after loading the weight, what we do is the last line is what we really test. And what we are trying to see, let's plot the curves. As you can see here, this is the plot I was showing you earlier, that the training loss will keep reducing. It will keep memorizing, what we call overfitting. But after a point, validation loss stops. And usually people say this is the point where we need to stop training, because after this, really the machine is not learning anything as far as new data is concerned. What else? So let's see, test data. Okay, that finally they're saying let's use the test data to evaluate your performance, and you'll do it only once. Remember, the test data was hidden, and you see my error is 81.61, and at some point they will probably be getting the equivalent accuracy of it. But these days, those are all standard functions. Okay, I have 3 more minutes. I'll show you the other code which we have, which is, if you were in the other classes and other workshops, you already know this one. So the second code I have is, this is how, if you want to use one of those standard large language models, and how do you call them? So open in Colab again, it's called training_transformers. Remember, everything is a transformer. What you do here is pip install transformers, and currently we have separate, like at least this is from code from, let's say, 2017, where you were allowed to call pipelines for separate tasks. So you can create a pipeline for classifier and give it 2 sentences. I've been waiting for this for all my life. I hate this so much. And the machine will reply saying, hey, the first sentence has a positive score, and I think I have a 95% confidence in it. The second sentence is a negative sentiment. I have 99% confidence on it. So you can just play around with this. This is where all the original BERT-based models, remember, this is pre-LLM. Now, if you scroll down, I have added, even OpenAI's GPT has ability to just tell you whether the sentence is positive or negative sentiments. Remember, these large language models inherently have all these capabilities. So at the end of the code, I have given examples of how even OpenAI GPT can answer this question. But what people have done is they put a chatbot around it. And the stronger capability is what we call the generative capability of these models, by which the machine is now able to answer like in a human-like form. To end, I want to give some shameless self-plug, which is, this is a tool we developed here in University of Arizona. You might know, some of you might know, it's called AI Wording. And this is, you can, as long as you have a University of Arizona login, you can log in here, or maybe you might want to drop me an email. If you log in and you don't see any of the chatbots, drop me an email. I will put my email address in the chat window here. I can add you to one of the systems. Okay, so what we have here is we have a lot of these professors who are using it for a lot of courses. Like this course is being using this for very focused on their own, like we do a RAG over it. You, as a general user, we will add you to, you can tell us what model you want. There is close to 75 models. So by default, we add you to Meta Llama. There's Llama's 3.1 instruct quantized. So you can have a chat window asking, hey, when does the sun set today, or some crap like that. But the most interesting part, oh, great. Maybe we made it focus on something very specific. The more interesting part is all these models 70 plus models can be accessed from command line. If you are interested, we teach that in our advanced level generative AI course. I will also put the link to that here. That has a lot of notebooks where you can access any of this particular link here. I'll put it. This has a lot of this code which using AI Verde, how we can. There is a lot of text-based mechanisms. There are some code where you can what do you call that? Upload images. So I suggest attending generative AI lectures. But yeah, that's all I have for today. We went through quickly training, testing, which is, like I said, you don't need it anymore. But yeah, that's how it works internally. Questions? I can't find the chat window again. Okay, Nicholas, in RAG, are there ways to mitigate the issue of final prompts sent to the model becoming too large beyond the context length? So that is the million-dollar question everybody's trying to figure out. I have come up with some techniques which are more like I encrypt it or compress it using standard tools, and I tell the machine, hey, here's a compressed text, like it still isn't plain text, like a SHA-256. The SHA is not reversible, but you can search for homomorphic encryptions. That's what I personally do. I put homomorphic encryptions with plus compression algorithms. So, and what I tell is, instead of my, let's say, 128K tokens, I have a 10K token. I send it to the machine and I say, hey, here's a 10K token, here's the key. You decrypt it, you decompress it, and you tell me the answer. It works really well for me. But that is a million-dollar question. Like every model has its limitations, and everybody is trying to find the next token limit. But give it a thought. Like think of it yourself. Like what would you do to reduce the size of a machine? There's so many of these codes, like Manchester coding, this coding, that coding. I even use something called quantum NLP coding. And these machines already know it because they have seen it. So try those ones. Yeah, welcome. Thank you. And between all our workshops, I hope you're learning something new and helping in your getting a job or whatever it is. And if you're from computer science, I also want to point out one of the courses we did a couple of semesters ago. It's called Cracking the Coding Interview. Because even if you are applying for AI software engineer jobs, sooner or later you will end up encountering algorithm-based questions. So if you are interested in that kind of a course, we also have it in the UA Data Lab. I think if you, am I sharing my screen? I am, right? Okay, so if you go back to repositories, we have, I think there you go, cracking the coding interview. We did that for an entire semester. A lot of tricks and techniques, which helped me get a lot of job offers when I was a master's student. So do check that out also. All right, that's all I have. Thank you all. Thank you.